Welcome to the Green CE movie series. This presentation documents the design, construction, and occupancy of the Health Sciences Education Building. We will utilize a case study format to better understand this exciting and complex project. The University of Arizona College of Medicine Phoenix has partnered with Northern Arizona University to create an innovative model for an interdisciplinary approach to health sciences education and research. The two universities, each with distinct institutional cultures, will collaborate on one campus, the Phoenix Biomedical Campus in downtown Phoenix at Copper Square. The city-owned Biomedical Campus is a 28-acre urban medical and bioscience campus planned for more than 6 million square feet of biomedical-related research, academic and clinical facilities. The campus aims to have the highest concentration of research scientists and complementary research professionals in the region. Phoenix is the capital of Arizona and the state's largest city, with 1.4 million people and a total metropolitan population of just over 4.3 million. With a huge land area of 517 square miles, the city has a low density rate of about 2,797 people per square mile. As a point of comparison, Philadelphia has a similar population at 1.5 million, but a density rate of over 11,000 people per square mile.
The City of Phoenix owns the land of the Phoenix Biomedical Campus. We have been assembling property over a number of years, created a genomics research facility, built it, Howell's 5 genomics research institutes that brought the attention of interest of the U of A up to Phoenix and to site the medical school and some historic buildings that are part of this campus. And this is the next extension of the development of the Phoenix Biomedical Campus and the extension of the medical school.
Historically, campuses really are great transitions between what we call the town-gown relationship. It really helped to pull that together here. The scale is lower. The scale is a nice transition between those two. The idea of having an element in that location where there's always going to be activity going on is another great thing, and so it really starts to blend those two things together. By having a campus, you can really control the flow within the campus and through the campus, and so we're able to maintain the grid of the city through there without really disrupting that. And so what it does is it creates the element of surprise. You know, suddenly you're on a campus and you weren't really expecting that, but hey, this is kind of cool, and then you move through and you're downtown.
The new copper-clad Health Sciences Education Building, or HSEB, will support the colleges of medicine, pharmacy, nursing, allied health, and biomedical informatics for the University of Arizona. Northern Arizona University will offer its new physician's assistant and occupational therapy programs, as well as an expansion of its existing doctoral program in physical therapy at the new building. When completed, the 268,000 square foot, 6-story facility will provide learning environments to train 1,200 medical professionals.
One of the major issues, one of the major goals of this building was to build and construct a building that could be used in what we refer to as interprofessional training. That is, all the different health disciplines being able to interact while they're being educated within one space. So in this new building, we're going to be seeing medical students, but you're also going to be seeing physician assistant students, physical therapy students, eventually pharmacy students, public health students, maybe nursing students, that will all interact in the educational setting, which really will prepare them for the real world. Right now, most of those health professions are taught separately. We know that everyone works together when you get out into the real world. The doctor is alongside a nurse, which has to prescribe something that a pharmacist is going to fill. But those disciplines are not taught together. This building allows for interprofessional training right from the beginning so they know how to work with each other when they get out. This is a great place for them to start. They're going to spend their first day in the profession in this building. Their first day of school, their first day of lab work, their first day of study in the library is going to be in this building. Someday they're all going to take care of us. We'd like to think that we're giving them a great start in a great facility.
The city of Phoenix is located in the northeastern extents of the Sonoran Desert. The temperature reaches 100 degrees on average for 110 days of the year. Highs top 110 degrees, an average of 18 days during the year. The rapid expansion of major urban areas in Phoenix has caused a significant urban heat island to develop, causing even the daily low temperatures to be abnormally high. Both universities have adopted a goal of LEED Silver as a minimum for all buildings. The HSEB is registered under the LEED for New Construction, version 2009 rating system and is currently attempting 66 points. Sustainable sites. The owners have selected a previously developed site in a dense urban area that has access to public transportation. By providing open space and restoring the site with native plants, improving the quality of stormwater runoff, and mitigating heat island, the project has addressed a vast range of environmental issues associated with the project site. The city's strategic vision for the downtown area where the HSEB is sited includes goals of density, community, and mixed-use development. The siting of the building originates from the master plan by Ayers St. Gross that establishes a north-south central campus green. The green connects the historic buildings, located to the south, with current and future research facilities to the north. The site of the HSEB is on the southeast side of the campus, where a parking lot was once located. It is bordered by a busy street on the east side.
The City of Phoenix is on track with this in terms of how important the density is in building up downtown. The city has introduced what's called the Downtown Code, and it's not for the entire City of Phoenix out to its limits. It's being defined to what we're calling the urban core downtown. 7th Street, I think, over to the 7th Avenue, and our campus is in the middle of it essentially. And so the guidelines that are put forth in the Downtown Code apply to our projects. In general, it's all about density and building to the property line and creating landscaping and doing all you can to create shade. Shade, if you haven't been here in July again, you need shade when you're walking downtown. Trying to get more people outside and to use downtown year-round, and the way to do that is to create shade. You've got to get some shade on those sidewalks, whether it's from taller buildings closer to the property line to tree-lined streets. You have to do what you can to create some comfort out there.
We've assembled 30 acres of land to create this biomedical campus. The site this facility is sited in the center of that. So it was important for us that we maximize the resource of the land. The difficulty of assemblage and the price of assemblage really predicated that we needed to build up in greatest density that we could, working through the programmatic constraints of moving students through a building. Going into a high-rise condition is difficult. Obviously, higher priced construction, going to high-rise zoning, building code conditions, etc. So I think the project's really created a good balance with maximizing the finite resource of land availability with density that the project is achieved, and a good floor-to-area ratio, and likewise balance and symmetry to the campus. We've got the TGen facility, it's in similar height, stepping down to adjacency to the historic buildings as well. So I think the projects have created a good balance on the campus in those aspects.
The HSEB will take advantage of the on-campus and multiple building certification program for LEED certification. This LEED program helps project teams more easily and efficiently certify multiple projects located on one site and under the control of a single entity. The program's goals are to encourage a holistic, sustainable approach to project management, address the unique challenges and opportunities inherent in campus projects, allow project teams to document a credit once for the entire campus, capture economies of scale in the certification process through shared credits. The majority of the credits in the Sustainable Sites credit category will be achieved using the campus approach. In addition, water-efficient landscaping, refrigerant management, green power, environmental tobacco smoke control, and a green cleaning program are all implemented on a campus-wide approach.
The site previously was a parking lot and not making the best use of the land in downtown Phoenix. We, along with the design team, decided to use this particular portion of that parking lot for this building because it related most to existing buildings on the site. Very important to make decisions for urban infill as opposed to a greenfield build, especially for a building that's so integrated with health sciences and education. Educating people about this site choice is very important.
Energy and atmosphere. Reducing energy use in an extreme environment is a priority. The team uses the integrated design approach and early energy modeling to optimize the performance of the building. The desert is relentless and harsh, yet hundreds of generations have subsisted here, adapting to the ecosystem through respectful, practical, and sustainable practices. The design for the Health Science Education Building was shaped by the desert climate and the goal of reduced energy consumption. The facility is organized into east-west wings connected to a north-south axis, establishing the eastern boundary of the campus. The building's form and its orientation result from efforts to minimize the intense effects of the Arizona sun.
The overriding ideas behind this building was that this was going to be a building that could only be built here and nowhere else, and it should look like that. And you know, that derives from its relationship to the place, what's important around it, but also its geographic nature. So, you know, this is fundamentally a desert landscape, and the sun is incredibly intense. So the design of the building is really formed by that. If you see the building, basically the building is elongated in the east-west orientation. The idea being that you get predominantly north and south elevations, because those are the easiest to treat here. You know, the north has just a little bit of sun coming around, and the south, the sun is fairly high. So with sunshades, you can really design the building fairly easily to protect that. But the east and the west are much more problematic because the sun is really low. And so we try to eliminate, for the most part, east and west windows. And so you'll see there are these kind of incisions into the building where we needed light. And you can see that in the Learning Resource Studio, the library up on the 3rd and 4th floor, where you have these big sort of insertions so that even though we need light from the west, we get it from the north and south. And also on the east, we have these big insertions. Basically, we have these big walls that are all copper, but we have these cuts in the building that give light into the building where you need it. And then we have that big canyon. You know, the description that I gave of how the building evolved and affects how the building sits on the site. And it's more a passive approach to doing the right thing in terms of energy consumption. And LEED has, you know, scores in terms of energy consumption. So that, you know, from the outset, that was one of the biggest factors in terms of LEED for us was, you know, to try and minimize the amount of energy that the building consumes.
Early in the design phase, the team turns to energy modeling in order to optimize the performance of the facade. The first step in developing an accurate and informative energy model is to establish the best climate data for the location. The relevant data that was evaluated includes 1. The monthly mean temperatures, which peaks at a high of 115 degrees Fahrenheit. 2. The annual hourly temperature and humidity. Phoenix is typically a hot, dry climate, but there is an official monsoon season in which humidity reaches 60% RH with an outdoor temperature of 100 degrees Fahrenheit. This condition proved to be the worst-case design condition. 3. Sky temperature. The sky temperature is consistently 25 degrees less than the outdoor air temperature. Although this provides an opportunity to reject heat to the night sky, high evening air temperatures will reduce the effectiveness of thermal mass as a method of cooling, which relies on a long period of nighttime cooling. This condition makes metal cladding an attractive alternative due to its ability to quickly reject heat when not exposed to solar radiation. 4. Solar energy. Phoenix reports a substantial amount of global insolation, a source of load on the exterior envelope that will require significant control. 5. Solar shading. Studies of the monthly solar irradiation for shaded and unshaded vertical surfaces demonstrate that 70% of the solar energy is direct beam that can be controlled by shading. Providing a shading device with a 45-degree cutoff angle will reduce annual irradiation on a south-facing surface by 2/3, east and west-facing by 50%, and even north-facing surfaces by 30%. Based on the climate data analysis, 2 main objectives were set. 1. Prevent introduction of direct sun into openings on all elevations from May through the end of September. And 2. Base the envelope performance on 2 worst-case conditions: highest summer temperature, 115 degrees, and monsoon conditions, 60% relative humidity at 75 degrees wet bulb and 100 degrees dry bulb. Since optimizing orientation will provide the greatest opportunity to control loads from solar gain, the next step was to test various options for the form and orientation of the building. A series of geometric shading studies helped the design team understand which portions of the building will receive direct sunlight during the design period and what types of shading devices are most effective. The simulation package Radiance was used to estimate the daylight with detailed 3-dimensional models, including relevant attributes of the surface, such as reflectance and light transmission. These models also showed the effect of self-shading from the building itself and from surrounding buildings. The program Ecotect was used to show sun penetration at 3 important times of the design period. The geometric shading study led to 4 main design recommendations. 1. Orient the wings in an east-west direction to most effectively control solar gain on the building's facades. 2. Use self-shading to control solar gain by shaping the facade in 3 directions, which would entail: A. Curving the floor plates along the east-west axis, reducing the amount of sun on the east half of the south facade in the morning and the west half of the south facade in the afternoon. B. Sloping the vertical facade so that the upper floors projected beyond the lower floors. 3. Provide shading devices on all elevations to prevent introduction of direct sun into openings from May through the end of September. South facades could be nearly completely shaded with horizontal devices of various geometries. East and west facades should be opaque as possible, but if exposed, protected from low and high angle sun by honeycomb or screened structures. North facades receive low-angle summer sun and should be protected by closely spaced shallow vertical fins. 4. The courtyard would require protection from overhead. The design team adapts the design to these principles. Rather than a smooth curve, the north and south wings were bent into a bow tie shape, which achieves roughly the same performance while allowing rectilinear layouts of programmed spaces. Programmatic constraints would not allow the sloping of the vertical wall face, so the sunshade design parameters were modified to compensate. Next, the team will need to consider the program, daylighting, and views in order to implement the recommendations for shading and fenestration for each facade. In order to rapidly test various options, TransSolar develops a simplified approach where an individual model is created for each of the 5 major space types identified in the building program: offices, classrooms, clinical spaces, gross anatomy laboratories, and circulation. Each space is modeled as an individual, typically sized room within the building with 3 interior walls and 1 exterior wall with 60% glazed area. Various combinations of ventilation systems, thermal comfort controls, fenestration, and shading devices are modeled. The thermal simulation of these shoebox models was performed using Transys 16. The next study looked at the effect of daylighting on the design of the facade and composition of the elevations, with the important goal of projecting as much daylight deep into the floor plate as possible. While this at first appeared counterintuitive for Phoenix, it was justified by the reduction of electrical lighting loads and maximizing connections to the outdoors for the building occupants. The team configured shading devices to prevent direct sun from falling on glass from May to September. By using the shading devices as light shelves to reflect indirect light into the building, they also reduce glare. The program Ecotect was used to show sun penetration and generate sun angle studies to help configure the devices. Finally, an exterior wall section profile was developed for each of the major space types, configured for orientation, ceiling height, room depth, and room activity. These optimized profiles were then applied to the elevations.
Envelope performance of the building is huge. It's key to, from my aspect as an energy modeler, whenever there's a high-performing envelope, I get my hopes up for high energy savings, because it's where you can make or break a project. It can either use a lot of energy, or it can retain a lot of cooling, kick out a lot of heat. This project was great. AEI and the design team worked with a company, TransSolar, to do a solar study of the building. And what TransSolar, their report had told us, was that they were able to place glazing on the building so that in the summer there would be no direct solar radiation, no direct solar gain on glazing. And in the winter, the building was positioned such that the sun would actually heat the glass and actually provide a little bit of a heat load. And so it actually turned out to be, it doesn't hurt us and it helps us in heating or cooling season. What that means from an energy standpoint is that we now use less chilled water, which on this project it's purchased through a utility. So it means less of a utility bill, chilled water bill, not necessarily electricity. And on the heating side, we actually use less natural gas. So it was really, really big for something as simple as a window to equate to cost savings for chilled water and natural gas.
We used Transys and Therm and Ecotect, and basically the challenge on this project was finding the right modeling software at the right stage of the design of the building. So we used a series of, I think we used Ecotect at the very beginning to try and really optimize the shape of the building and optimize its orientation to the sun. And then we used it also in the design of the sunshades. For instance, one of the main criteria that we established was that the windows would always be shaded from the month of, basically from May through September, that the glass would be 100% shaded. And so modeling software was essential to be able to model doing sun path diagrams to essentially validate to the owner and validate to the mechanical engineer that he could be assured that the sunshades were designed in such a way that he knew that the glass would be shaded those critical 8 months out of the 6 to 8 months out of the year, so he could validate his energy model. We used a WUFI model, which is this program that is basically from Germany, but basically it's a hygrothermic analysis software that we used on the exterior wall itself, and often it's used in colder climates to figure out where the dew point is when you're doing a dew point analysis on a building. And in Arizona, that wasn't as critical, obviously, but we were able to use it when we were designing the exterior wall to determine the best location, the best type, and the best thickness, and optimize the insulation thickness in its placement relative to the membrane. So that's the software that we used to basically determine that the insulation was best not only in front of the membrane, in front of the waterproofing, to keep it at a constant and low temperature, but also to optimize what type of insulation and what the optimum thickness of that was. We thickened it up from what was normally required for the energy code. in order to make sure that it performed well enough to make sure that the waterproof membrane would not get overheated and would have a long life to it.
The design for the Health Sciences Education Building, HSEB, draws inspiration from Arizona's mountains and canyons and responds to the desert climate, characterized by intense sunlight and extreme temperatures. For insight and inspiration, the architects turned to early human settlement where Native Americans traditionally sought shelter deep within slot canyons that were naturally created by wind and water erosion. These self-shaded, majestic spaces maintain temperatures 15 to 25 degrees cooler than the ambient temperatures outside.
Honestly, my favorite feature is the canyon in the project. And I think it encompasses a lot of, or captures a lot of kind of a range of design issues, all the way up from master planning down to how it's detailed. The scale of it, the intent, the inspiration for it, from Co's point of view, was the kind of striations of rock in a canyon, and so they've kind of played that out in their material use going up and down the canyon, up the sidewalls of the canyon. Part of our master plan was to allow filtering of people, allow movement laterally across the campus. By putting a big blocky building there, you would be walking around at this. Our building, HSEB, is very porous at the ground level. You can move in all sorts of directions. It makes good connectivity east-west, as well as starting the path north for future buildings. And so it sets up a nice rhythm of sort of solid void in terms of occupied space and then flexible space.
A couple of innovation credits that I think we were going after, and I think when you go out and look at the courtyard, for instance, the courtyard is really seen. There's about one or two innovation credits there, which have to do with the fabric structure that covers the courtyard and the air conditioning of the courtyard, which sounds odd, especially in Arizona. But we really did a series of energy models and energy studies that showed that by layering on different technologies onto this central public outdoor space, we could actually take an outdoor space in an environment as harsh as Phoenix and really make it a pleasant place to be in year-round. And the way we did that in LEED terms was through the solar canopy, the tensile fabric structure that covers the courtyard. Because what that does, first of all, that just simply blocks the sun from entering the courtyard year-round. So that's the first and most important way to optimize the thermal comfort of the outdoor space. The second thing that we did was also the geometry of that courtyard. It's a very tall and narrow space, basically designed around the idea of the local canyons that you have here, which in the Arizona desert, the local canyons are the places where the Native Americans basically built their houses because they were always the coolest spot in the desert, very tall and always shaded. So we took that idea and translated that into the courtyard. So basically by modifying the geometry of the court, having a tall, narrow space that was covered against the sun, those were the first two things that we did to optimize the comfort. The next thing was we air conditioned the courtyard, which essentially means that the air conditioning system has a certain amount of air, waste air, that's basically rejected out into the atmosphere. It's the air, a certain amount of air gets recirculated back into the building, but a certain amount that basically is unusable is usually just rejected into the sky. What we did is we took that air and we, at certain times of the year, bring it back into the courtyard. And even though that air that's coming out of the offices or out of the classrooms is maybe 80, 85 degrees, when it's 105 outside in that courtyard, even though you don't have the direct sun, you're still pumping 80-degree air into an area that typically is 100, you're reducing the temperature of that outdoor space. And so that was another one of the innovation credits that really go into a whole system. It's really a whole system of really 4 different technologies in that courtyard. The shades, the envelope or the shape, the air conditioning, and then the thermal mass, the concrete block which defines the courtyard, and the materials. So it's really 4 things that really don't add up into an individual credit each time, but they're 4 things that we still felt were important to do anyway, even though maybe only 1 or 2 of them will really result in a LEED credit.
One of the things that was very important for us was to do this kind of connecting bar that goes in the north-south direction. So we have the library there. You know, that's where all the students will sort of congregate and will eventually connect to the new buildings that will be going to the north of the building. How that works, it's really quite terrific. And the canyon, I think, will become a great space where students will be able to hang out. And I think in this climate, you know, we thought that we could have a really tight space, and high and tight, so that the sun wouldn't get into it. And we modeled it, and that's why we're now putting on these kind of sails up at the top to keep the sun away from indirectly. And also that the material is different on the inside there. It's a masonry, it's a concrete block, which has thermal properties, you know, better thermal properties in terms of mitigating the diurnal range. You know, it traps the heat, stores it, and then releases it much more slowly than a cavity wall. So the idea was we have these masonry walls in that canyon, and on the outside we'd have this copper.
We use plants that are native to the region, and we wanted to showcase those within the canyon portion of the project. These plants are shade tolerant. They're a little bit more adapted to the low light levels that will be in the canyon, and so we really tried to make sure that we matched the light level, the sun exposure, to the plant material on site, so that we didn't have plant material failure, if you will.
In addition to the early energy modeling performed by TransSolar, the mechanical engineer must quantify the predicted annual energy cost for the building to demonstrate a level of compliance with Energy and Atmosphere Credit 1. Optimize energy performance.
This project actually started in 2007. And so through various starting and stopping and design phasing, there was some early energy modeling, but the real push to do, you know, to get a solid model going was towards the end of DD. The mechanical engineer would come up and say, hey, we had this meeting and we were, you know, threw out an idea, and where would this put us? You know, how would this, you know, affect the model? And it might have been something as simple as, you know, one glass type compared to another, or, you know, the shade compared to another one. What did actually happen was to take that on the other side, and during submittals, you know, the contract, you know, we spec'd this, the contractor is proposing this. They're saying the cost savings is there, what does it do to our energy savings? And so, you know, it was definitely kept in mind that, you know, if we can do it, if we can get the same performance for less price, you know, let's entertain that notion. But it always came across my desk of, what does this glass do, or what does this do to our energy savings? And so that was using energy modeling, not necessarily to inform design, but almost as a VE tool. The chilled water on this project is actually purchased through a central utility. And in Phoenix, there is a central utility downtown that has infrastructure to most of the buildings downtown. And so it was very easy for us to tap this building into an existing chilled water line, and they meter it just like a water meter from your utility at home. What that does is it measures flow and delta of the temperature difference in the pipe. So they actually bill based on how much energy you pull from the chilled water, not necessarily flow. And so it was easy for a building connection, but it was challenging for energy savings because just how it's modeled, the building is no longer a standalone system. It now relies on a utility plant that is a few miles away. The refrigerant management prerequisite was met because the utility takes very good care of their equipment, and they make sure that they have low ozone depleting potential and low greenhouse gas refrigerants. But because we modeled a district energy, a district chilled water, we now needed to take into account the downstream equipment and the upstream equipment for enhanced refrigerant management. And so because there was a chiller, there was refrigerant, and we actually didn't qualify for it. Difference between energy cost reduction and energy savings reduction is one that I struggle with as an energy modeler. Mostly because if you have a system that is very efficient and reduces energy, but it uses, on this project, for example, the cost to connect to chilled water is at a premium, and actually the chilled water costs more than the electricity. And when you break it out unit for unit. And what that means is that while we use a more thermal efficient system in chilled water, it's better for energy transfer, we're actually being penalized from a cost perspective because we've reduced energy, but we've actually, I don't want to say increased cost, but we haven't reduced it to its maximum.
Materials and resources. Priority is given to materials that are durable and high in recycled and regional materials. The team also sets high goals to divert construction waste from the landfill and source sustainably harvested wood. The topography of Phoenix is flat, but the city is surrounded by mountain ranges. The material choice for the external skin that wraps most of the building derives from the regional connection of Arizona's abundance of copper ore, its durability, and an innovative adaptation of skin technologies and manufacturing capabilities. Conceptually, the skin is a permanent sunscreen, an SPF that never wears off. Taking its cue from the functional form of local vegetation, the copper sheets are manipulated akin to the flutes of a saguaro cactus to absorb less direct solar radiation. The copper panel's form and color correspond to the nearby geological formations in the mountains.
We considered several different skins, and they came down to zinc and copper. Copper is one of the 5 C's in this state, and so we felt that it would best represent the architect's vision. He had presented what he thought the building should reflect. It's a building for Arizona. It's not just Phoenix or the University of Arizona. This is a building because kids from all over this state are going to be going to med school here. So that's the vision he wanted. And when he presented this, I think that I'd have to say there was excitement from day one. I mean, this is one of those that just reached out and grabbed people from the very beginning. Fortunately, hit the low point in copper. It was under $2 a pound when this was being considered, and both the architect and the contractor in particular came forth with a plan that said, we should just pre-purchase all the copper for this project. Pre-purchase it right now, today. And we took it back down to the university level and talked about that and said, yeah, this is a great idea. We can do this. And what a building it's going to be. So that's kind of how the idea evolved into the reality that you see out there right now.
The other thing that's regional, that's different about this building, was that this copper is a regional material. It happened to be relatively at its low point in terms of cost, so we could afford it. It was a local material. But we tried to get a building that kind of connected with the surrounding mountains. If you look, a lot of the views around here are of the mountains that surround Phoenix. And we wanted the color and the striations to relate to those mountains. And so, we did a lot of design investigations at the outset, and as I mentioned, originally we were looking at rusted steel, but that had its own problems. We wanted that kind of color. And we realized we could get that with copper because in this climate, it's not going to turn green, it's going to stay brown. And with these folds, we designed about 26 different panels that we did in different combinations and had we worked with the subcontractor, Kovach, to determine what was possible and feasible to make, but we made these different panels and then we arranged them in different ways so that you get these kind of striations in the building that kind of look like the striations in the canyons that you see around here, the kind of stone striations. That's basically the idea behind what the building looks like in the copper. I think as time goes on and the copper starts changing color and gets more variegated, it really will feel a bigger connection to the sort of surrounding mountains, and hopefully it'll become much more kind of apparent what we were trying to do.
The vision that Kovach had for the HSEB project was to come up with something that had never been done before, that could never be replicated again, and to accomplish the design intent and really bring that design to reality. So where did the copper come from in the first place? The copper on the HSEB project is 99% recycled material from U.S. copper mills. Very likely that copper was parts and pieces to computers, plumbing fixtures, wires, etc., that saw a life cycle for the last 30 years before it was recycled into copper that was shipped to Arizona and manufactured into the panels on the outside of the HSEB building.
Once we knew we were using a copper cladding system, we tried to come up with a technology or a way of using it that we felt was really smart and really suited to the local climate. So we basically adapted rain screen technology and really used it as a sunscreen for that matter. So we took a system that's traditionally used in the Northwest or in Europe, which is really about keeping the water out, but we actually used it as a way to keep the sun really out of the building. And so in this case, as you'll see, the copper is really used as an exterior cladding material. We basically build this sandwich wall where we have the exterior structural wall, a waterproofing membrane, a layer 4 inches of rigid insulation, a 2-inch airspace, and then the copper itself. And by doing that, what that does is that the copper and the airspace work together in order to absorb the radiant heat from the sun and take that heat and allow it to travel up through that airspace and vent out the top of the building. The insulation then works to also not only insulate the building, but what it also does is, because it's in front of the waterproofing, it protects the waterproofing from getting hot, which obviously in Arizona is very important. So we were able to do a series of thermal models that demonstrated that when it's 180 degrees on the copper surface itself from the sun hitting it, the waterproof membrane itself never gets above 80 or 90 degrees and is able to operate within a temperature that makes it last a full 20 years. So had we put the insulation behind the membrane, which is something that was typically done in Arizona, and I think that the system that we used to attach the copper back to the building and try to minimize thermal bridging, for instance. You've got a material like copper which gets very hot, it absorbs heat, but we worked very hard to put thermal isolation or isolators between the copper and the support structure that holds it up, and to take that support structure and embed it within the insulation. So it's really not just the copper itself, but the copper, the supports, the insulation, and the whole assembly itself, and using the air cavity that is really normally part of a rain screen to also basically take the rain screen and make it into a sunscreen. So the copper is really part of an entire integrated 5-component assembly that really drains the water out and also drains hot air out and prevents the transfer of heat from the copper to the support structure in a number of different ways. So it's really a fully integrated assembly and a fully integrated system that I think is really going to perform really well.
Maximizing the integrated design process was essential to the success of the health science education building. It meant assembling a team of experts including the design team, construction manager, and exterior envelope contractors, who understood the project's goals and were prepared to contribute in their particular areas of expertise. The sustainability goals and resulting performance criteria were defined early, during schematic design, when the construction manager was brought into the project.
The value, I think, of LEED is that it really forces the owner and the architect and all the entire design team and the city and everybody to really get together and focus on what is really important and set priorities for the project. And whether the building gets, 50 points or 56 points, the value is that it really gets everybody together and it forces everyone to sit at the same table and speak the same language and prioritize and decide together as a group what are the priorities for the project. And that, I think, has tremendous value.
Well, the integrated design process is vital when you're working on a project of this scope. The site is very sensitive, so working with a civil engineer to understand runoff and retention requirements, working with the architect to understand anticipated traffic flow of patrons or students, administrators, not only into the building but around the rest of the campus was very important. So understanding what their goals and objectives were important because that really informs what we do with the site design. It's all in response to what the program is for the building, what the mission is for the client, and so we really need that information from people that we collaborate with. Co-architects had a great vision, both in materials and in visualizing what the building would be and what the space would be and the site would be. And so we really tried to implement that with our landscape design.
The building would not have the same appearance, it would not have the same result if we did not have the entire design team or the contracting team on board from the beginning. It was absolutely essential that we had the subcontractors, especially the metal panel, the copper cladding contractor, and the curtain wall contractor on board while we were in the design stage. Their ability to help us understand the relative costs of the different systems and weigh different options, look at different ways of building the building and optimize the performance of the building and bring the building in on budget. Could not have been done if we were designing the building in a vacuum. If we were just designing it in a traditional design bid build fashion, for instance, the building would never have looked the way it does today.
Another aspect of the integrated design team is the integration of the contractor with our team. And that's something that we've been doing a lot recently. I mean, the industry in general, the profession, has gone that way, and it really has helped the building because what happens is, even during the schematic design phase, the contractor's on board, and they give us input in terms of sort of the cost effectiveness of certain strategies. And even down to this, they get subcontractors who work with us, and when we detail the skin, like the copper, or where the mechanical rooms, the systems parts, they had a big impact in terms of making it a cost-effective decision. So for instance, in the mechanical room, we have a distributed mechanical room on every floor, as opposed to having it on the roof. That's has a lot to do with the contractor being involved. And also, when you have a contractor that you have a good relationship with, like we had on this job, they become your advocate in terms of saying that they can afford to build what you're doing. They made the client feel at ease that they could get this building at the cost. And they're doing these sort of, it's almost like a menu. As we're doing design, there are certain elements that we want, and they're costing it, and they sort of say, okay, you can get this, but you can't get that. And together we sort of say, well, this is important to us, let's do these things. And that's how the integrated process works, which is really pretty terrific.
It was a collaborative process, so either the architects would come over from California here to our office in the Valley, or we would fly over, the construction management team, to their office in California. And this was done on a weekly basis just in order to share and collaborate. We also used our subcontractors as a collaborative design assist as well. It worked very well. We had some early subs that we brought on to do design assist, the mechanical and electrical subcontractors, as well as the KT Fabrication, who is doing the glass and glazing, and Kovach is doing the metal panels, the copper panels themselves. Brought on early to do design assist. And what it did is allowed the architects to use the expertise of the subcontractor during the design process. and tell them what would work and what wouldn't work. Real easy to draw a line on a piece of paper, not necessarily that easy to put it in place out in the field. So,
a major hurdle for the team is the significant decrease in budget that occurs after design has begun.
The project has gone through a lot of iterations. When it was initially awarded, it was in the neighborhood of $330 million. $480 million total project cost. That included 2 buildings. Our HSEB was supposed to be 440,000 square feet, and then there's a whole other research building called ABC2 that was a part of the project. That eventually fell away as funding from the state was dwindling. In the period where we were getting from 440,000 square feet down to 260, the building took on many, many forms you may have seen from Co. There were versions of the footprint that stretched all the way across the property over to 5th Street. And so it was really spanning the entire campus laterally, and that was really a part of the master plan too, to try to do that. By the time the square footage was reduced, the building was becoming too short and too low slung. It really wasn't accomplishing any of the goals the city may have had with regard to density and height on the campus. And so we sort of packed it back together and made a larger, more sensible building and preserve a site for future building on the other side of the campus. And so that, from a master planning standpoint, we're able to sort of follow through on some of the tenets of the master plan.
So in conjunction with the contractor, the architect, and the subcontractors, who we have on board very early in the process for design assist, because cost is such an important component of designing a building, that we go through the process as a team. We incorporated BIM, building modeling, very early, from day one. And that in itself lends all the team members to certainly pay attention to how the design is evolving, but also the cost of the building, because everyone has a stake in that. Certainly study design alternatives. From day 2, we set out this grandiose design, and then from day 2, we incorporate design alternatives, value engineering, and go through that process. But everyone certainly pays attention to the process, and probably more importantly is invited to the process. We take great pains to make sure that there's involvement by all team members from the very beginning. Budgets are always challenging. This building started out with a certain budget, and then we had a couple of ripples that turned into tsunamis. Very, very challenging budget climate, but again, through the value engineering, we got through those. But I would say that that's the biggest obstacle. You have the vision, and you have the budget on day 1, but it always changes.
Indoor environmental quality. For the owners, it is vital that the interior of the building enhance the learning environment for the students, while also raising their awareness of the effect the indoor environment has on their well-being.
We needed a facility that's going to be very welcoming to medical students. And welcoming is a word that encompasses the technical side of the building, but also the atmosphere in which they learn. Medical students typically spend an awful lot of time at the facility where they're learning. Whereas I said earlier, this is my home, their home's the library, the medical library, the lecture halls, the clinical studies. Pick the part of the building, they're going to be living there, except for gross anatomy, but they'll spend time there.
Regional priority. The team has given emphasis to implementing environmental strategies that are encouraged by the regional priority credits for the location of the building. The HSEB project is attempting 11 of the 14 possible credits in the Sustainable Sites category. In the Water Efficiency category, the project is pursuing water-efficient landscaping at the 50% level and indoor water use reduction at the 35% level. The USGBC has identified promoting density and community connectivity, reducing heat island effect, reducing parking capacity, and water conservation as some of the most important environmental strategies for the Phoenix region. By achieving credits in the LEED for new construction rating system related to these strategies, The project will be able to receive up to 4 bonus points.
Most important LEED credit in Phoenix is the shade credit, especially for a site-specific person like a landscape architect. We had an integral role in deciding the tree spacing and also defining a tree green belt that would stretch from the entrance of the HSEB building all the way to whatever happens in the future at the north end of the campus. So that, along with the architectural shade canopies, low reflective materials, making sure that we had a nice shade-rich environment, especially in the summer in Phoenix, was very important to us and something that we took an integral role in. We utilized stabilized decomposed granite on this site as a major pedestrian thoroughfare. However, it's a material that we can use here in Phoenix because we don't have snow concerns. We don't have as many puddling concerns. It's a permeable surface, and it's got a low SRI, and we were able to take advantage of the stabilized DG to contribute towards our shade credit. So we have a very compact site, and so one of the things that we've done is make sure that any runoff is going into a landscape area or into a permeable paver area. So we're dealing with a lot of the water runoff on site. Phoenix has a requirement that the first flush is contained on site, and so we've adhered to that. I think it's an important aspect to not have your runoff be someone else's problem. So we've taken an approach to contain all of the water runoff on site using our retention basins, using landscape areas, and using permeable paver areas underneath vehicular driving aisles. Some of the biggest LEED credit challenges on the project were ensuring that we could capitalize on a water use reduction. Even though we have turf on the project, we're using a very small amount of turf over the vivarium structure. And so we're taking an area that isn't necessarily good for other uses and using it for turf. Turf uses a lot of water percentage-wise, but by keeping that amount of turf panel lower and using a lot of other native plant materials, we were able to reduce the water by over 20% as per the LEED requirement. Some of the native species in Phoenix are extremely beautiful, and so we've used Palo Verde trees on this project. We've used mesquite trees on this project, which were existing. Some other plants that we've used were Hesperaloe vinifera. We've used Hesperaloe parviflora. We've used deer grass on the project. And we've used these plants in masses so that as you're walking through, you'll experience different plants at different levels, and they'll repeat so that you're tied to the site a little bit more.
The LEED credits that we played a significant role in have been the prerequisite credit for construction activities, stormwater management, and then that leads into the stormwater quality and stormwater quantity credits. LEED credits oftentimes have synergy between them. On this project, we found as we tried to reduce the heat island effect outside of the building, that went hand in hand with providing a permeable pavement for parking at the site. LEED is valuable in a project such as this, as it brings to the forefront of our minds the need for sustainable design, and we can explore options such as permeable paving in lieu of asphalt, which reduces heat island and also can help in stormwater management.
The water savings in the building is accomplished through any number of low-flow fixtures, waterless urinals. When I say, the envelope is where you make up a lot of ground on your energy savings. Waterless urinals are huge in water savings. They are by far the lion's share of water savings.
But sustainability as a global concept was a really important piece of what we do as a campus. Recognizing that the world has some major challenges in the environment, in the economies of the world, and how we make a living, how we sustain ourselves as a species. We really began to recognize that students of this era need to be grounded and understand what's going on, be in a position when they leave the university, go into their corporate careers, go into their government careers, wherever they might be going, businesses, that they're the ones who will provide the solutions and be able to do that hard thinking that's needed in order for us to reach that goal of being a much more sustainable world. It's begun to infuse into any type of, almost all the curriculum. Even if you're a philosophy major or you're a history major or you're a business major, there is some component of sustainability or green that's built into your time at the university. Our goal is for all of our students to leave the university with sort of a baseline understanding of what's going on in the world in terms of sustainability, and then to go out and be a big part of the solutions that are created to overcome these big problems that we're facing as a world. Overall, probably what I like most about this building is the fact that we really took in the human dynamic in designing a building, and particularly when you know, one of the keys to green buildings or sustainable buildings is focused on the human. And it's not all about the aesthetics of the building or the performance of the building, the energy profile, which is really good on this building, obviously. Much lower energy use is the fact that humans will perform and thrive in this building. We do that, of course, through a lot of natural light. The studies have shown now, we've been involved in these studies with Stanford about the effect of green buildings on humans now for about 10 years. And the data is really starting to get much stronger that the people who can see natural light, who can see outside, perform better, are more alert, and learn better in the classroom. So I think that's fantastic. There's no volatile organic compounds in the building, so people don't get sick. You know, in the paints and the carpets, you know, the building is very quiet. It's designed to suppress noise because we found that noise is a stressor and reduces human performance. One of the things that we need to remember is this building is about healers, people who will go out as doctors and allied health professionals out on the front lines of healthcare, really providing you know, medical services and really being the next generation of folks who are out there serving as your doctors and our healthcare professionals. And so they're being taught in a building that is very sustainable and green, and we're hoping the fact that they've experienced that, and that will sort of build into their psyche. And when they're out, you know, working in hospitals and are the administrators making decisions, and clinics and offices, that they'll begin to incorporate these sort of values into their thinking and in their facilities, and they're putting sustainability into their practices as well. We'll just continue this great dialogue and process.
The design team has developed comprehensive strategies for sustainable site development, water savings, energy efficiency, material selection, and indoor environmental quality. Now the team shifts gears and proceeds to the construction phase for the Health Sciences Education Building. Join us for Part 2 and the exciting conclusion of this case study. Part 2 will focus on commissioning, measurement and verification, construction challenges, daylighting, and feature an extensive tour of the finished facility. We thank you for watching and wish you good luck on your next LEED project.